This movie will introduce the basic knowledge of the spectroelectrochemical method. The summary is as follows. The concept of spectroelectrochemical method will be introduced. Features and applications, classification, measurement principles, and comparison with conventional electrochemical methods. Spectroelectrochemistry is a general term for electrochemical method used to study the interface of electrode solution in situ or ex situ. The first spectroelectrochemical experiment was realized by T. Kuwana in 1964. For the first time, he used a light-transmissive electrode, coated with a thin layer of stannic oxide doped on a glass sheet, which acted as an electrode to measure the absorption of light by the concentration of electrically active substances in the electrolysis cell, thus pioneering the field of spectroelectrochemical research. Using a spectroelectrochemical cell, electrochemical and spectroscopic measurements are performed simultaneously, in order to understand the reactions and electronic states of molecules on the electrode surface, and electrode solution interface. Applications. For substances that are difficult to analyze electrochemically, if the reactant or product has spectral characteristics, the redox potential can also be calculated based on the magnitude of the absorbance. Spectroelectrochemical measurements of electrode systems in equilibrium or steady state can be used to identify molecular species in the stationary state, and analyze molecular structure and orientation. Spectroelectrochemical measurement, as a function of time, allows us to use spectral signals to track dynamic processes on the electrode surface at the molecular and atomic levels. Spectroelectrochemical measurements method is classified according to spectrum measurement cell, which can be divided in ex situ and in situ. Ex situ is a method to investigate the electrode by spectroscopic measurement outside the electrolytic cell, such as low-energy electron diffraction, X-ray diffraction, photoelectron spectroscopy, etc. The disadvantage of this off-site measurement is that it is impossible to accurately observe the status of some unstable electrochemical products or intermediates, which is difficult to meet the needs of research in electrochemical mechanism. In situ refers to the method of spectroscopic measurement carried out in the electrolytic cell, to observe the inside of the electrolytic cell, especially the electrode solution interface when performing electrochemical operation, such as on-site infrared spectroscopy, Raman spectroscopy, fluorescence spectroscopy, polarized spectroscopy, ultraviolet visible spectroscopy, paramagnetic resonance spectroscopy, circular dichroism, etc. The other classification method is divided into transmission method, reflection method, and parallel incidence method according to the light incident method. The transmission method is a method in which the incident light beam vertically pass through the light transmitting electrode and its adjacent solution. As shown in A and B, the reflection method includes the internal reflection method, C, and the specular reflection method, D. In the internal reflection method, the speed of incident light passes through the back of the light transmitting electrode and penetrates into the electrode solution interface, so that the incident angle is just larger than the reflection angle, and the light is totally reflected. The specular reflection rule is to let light enter from the solution side, reach the electrode surface, and be reflected by the electrode surface. The parallel incidence method, E and F, a light beam is emitted between an electrode and a solution near the electrode surface. There is also a classification method, which can be divided into thin layer spectroelectrochemical method, B and F, and semi-infinite diffusion spectroelectrochemical method, A, D, and E, according to the relative thickness of the solution layer near the electrode. The thin layer spectroelectrochemical method involves the exhaustive electrolysis of the active material in the electrolytic cell. Therefore, in general thin layer spectroelectrochemical experiments, longer excitation time is often used, such as longer electrolysis time in potential step experiments and slower potential scan rate in cyclic voltammetry experiments. Semi-infinite diffusion spectroscopy electrochemical experiments generally use a shorter excitation time. Commonly used electrical signals are single potential step, dual potential step, linear potential sweep and constant current. In this series we will introduce the basic principles of a transmission thin layer spectroelectrochemistry and their applications in electrochemical analysis. This is the overall schematic diagram of a typical spectroelectrochemical measurement system using transmitting electrodes. The basic measurement system requires a spectrometer, light source, transmissive electrolysis cell, potentiostat, and computer. You also need a circuit that can trigger the control, to carry out spectroelectrochemical synchronized measurement control. For a simple transmission experiments, a standard laboratory spectrometers can usually be used. There are many types of spectrometers. When combined with electrochemical measurement, the electrode connection for electrochemical measurement, the laboratory space and the difficulty of system installation should be considered. It is recommended to use a small spectrometer with a CCD array detector. Here, a schematic diagram of the internal optical structure of a small spectrometer is shown. The light is irradiated onto the collimator lens through the slit, refracted into parallel light, to be irradiated onto the grating. There, the light is dispersed into the monochromatic spectrum and projected onto a CCD array via a focusing lens for detection. This type of spectrometer typically performs spectral measurement control through computer-controlled software and has a trigger control function. The spectrometer is controlled externally through potentiostat control software to achieve synchronized detection with electrochemical reactions. For thin-layer spectroelectrochemical measurements, the electrolyte is typically injected into a thin quartz cell. The thickness of the liquid layer is about 50 to 200 micrometer. A transparent light transmitting electrode or grid-type light transmitting electrode is built as the working electrode. The light is irradiated in the direction of the electrode, the transmitted light is detected by the light receiving element, and the absorbance is measured. A thin layer of solution is used to quickly achieve complete electrolysis of active reactants in the electrolytic cell, minimizing the influence of active reactants in solution on absorbance measurements. The chemical species near the electrode can be identified by changing the absorption wavelength and absorbance. Next, let's compare spectroelectrochemical methods with traditional electrochemical methods. The electrochemical method describes the reaction mechanism and determines the kinetic parameters based on current and potential measurements, for example, current as a function of a series of parameters such as sweep rate, concentration, time, or electrode reaction speed, and then the reaction mechanism is deduced to determine the kinetic parameters. Disadvantages: it is this pure electrochemical measurement that lacks the characteristics of the electrode reaction molecules, that is, the current only represents the total rate of all processes that occur on the electrode surface, and there is no useful direct information about the reaction products or intermediates. Similarly, most studies on the electrode-electrolyte solution interface structure rely on capacitance measurement, and molecular level information cannot be obtained. Spectral electrochemistry has the following advantages over conventional electrochemical methods. First, it provides molecular information of electrode reaction products and intermediates, and can record the changes in the absorption spectrum of a substance on the surface of solution or electrode, while changing the application of an excitation potential signal. The intermediate reaction and the useful information of the intermediate molecular spectrum can also be monitored. Second, high selectivity. Spectroelectrochemistry not only uses electrochemical substances with different redox potentials to control, but also uses a variety of substances with different molecular spectroscopic properties. Many electrochemically indistinguishable electrode processes can be distinguished by spectroelectrochemical methods. Third, it is unaffected by charging and residual current. Spectroelectrochemical monitoring is the change in the spectrum of an electroactive substance. It has no effect on the measured optical signal, as long as other coexisting materials do not interfere with the spectrum. For example, in an indirect electrochemical reaction of a protein added to an electrocatalyst, the redox of the catalyst has a large background current. Voltammetric studies of the thermodynamics and dynamics of protein redox are difficult. Monitor protein properties using spectroelectrochemical methods. The change in absorption spectrum is studied without influence of electrocatalyst medium. Fourth, we can study very slow heterogeneous electron transfer and homogeneous chemical reactions. For example, the first electronic step of reduction of vitamin B12 is so slow that no reduction wave is observed, even at the slow potential sweep rate used in polarography. Whereas, in thin-layer spectroscopic potentiostatic experiments, shows two consecutive distinct electron steps, which have little effect on the currents obtained by the slow backward chemical reactions. Fifth, the adsorption orientation of electroactive substances on the electrode surface can be investigated. For substances that have spectral absorption in the UV visible region, the adsorption amount and adsorption direction of the adsorbed substance on the electrode surface can be determined from the change in absorbance of the light-absorbing substance in the solution before and after adsorption. In creating this material, we referred to the following references.